I'm Kevin, and today I'll be talking about an idea so important that it is one of the foundational principles of quantum physics, yet so controversial that Einstein himself never fully accepted it. Known as the Heisenberg uncertainty principle, it states that we can never exactly know an object's position and momentum at the same time. There is always this fundamental fuzziness in these properties. The principle is mathematically given by this inequality, where uncertainty in position times uncertainty in momentum is greater than or equal to this small fundamental constant. From this, you can clearly see that since neither uncertainty in position or momentum can be zero, there is always some uncertainty in these properties. You can also see that as one increases, the other must decrease. As we know more about one, we must know less about the other. In our daily world, this fuzziness or uncertainty is too small to see, but it becomes very prominent in the quantum realm.
For example, if I shine a beam of light through a slit, as the width of the slit gets smaller, an increase in the certainty of position, the light projected onto the screen gets wider, a decrease in the certainty of momentum. Another example are atoms. Why don't they look like this? After all, protons and electrons attract. Well, if the electrons were on the surface, they would have a certain position, so they must have an uncertain momentum.
But why? Why do position and momentum have this trade-off relation? The answer lies in something called a probability wave.
A probability wave just tells you the probability of an object existing at a certain point in space-time. As this wave gets smaller, the object's position grows more certain because all of its high probabilities are centered around one point. As this wave gets bigger, the position becomes less certain, but its momentum becomes more. How? Well, for really small particles, where the effects of the uncertainty principle are mainly visible, momentum depends on the wavelength of their probability wave. This wavelength certainty depends on the probability wave size. So, as the probability wave grows bigger, the wavelength becomes more certain, and since momentum depends on wavelength, the momentum also becomes more certain, but its position grows less. Likewise, as the probability wave grows smaller, the position becomes more certain, but now wavelength is uncertain, so the momentum becomes uncertain. To summarize, as the certainty in one increases, the object behaves more like its corresponding probability wave, and thus we can say less about its other property.
This profound relationship arises from probability waves, but in fact, the uncertainty principle is a fundamental characteristic of all waves. All waves have intrinsically fuzzy properties. This uncertainty contradicts Einstein's belief that the future is set in stone, and it implies that we can control our own futures. But which is right? Einstein's predetermined future or Heisenberg's undetermined destiny?